do some revision questions and doubts again today. So just putting up few questions for you to go through on the board. Okay, so in this particular example, we have a system of 4 plates forming 2 capacitors. Which are connected like this. Now given to us that all the 4 plates have the same area, but this has a distance d and this has a distance 0.8 d. So given that epsilon naught A by D is equal to 16 microfarad and this EMF is equal to 20 volts. Now also initially, so this is initial state. So this plate number 3 is given some net charge. So plate 3 has a charge Q naught of 24 microcoulombs. Okay. Now the switch S is closed. So find the heat dissipated in the circuit. How much heat is dissipated in the circuit after the switch is closed? Okay, so what you have to do first is now you have to understand how the charge will redistribute. So first thing you have to do is see distribution of charge before the switch is closed in the system. Okay, then eventually what you do is you understand that after the switch is closed, then in steady state what is happening. Okay, then find the steady state with the switch closed. Okay, so that will tell you how much charge is circulated by the battery, by the cell, how much charge is circulated. So then work done by the cell is equal to change in potential energy of the system plus the heat dissipated. So this concept you have to apply over here. Okay, so if you're working on the question, just continue. I'll just give you basic idea. So what is happening is before you close the switch, now it is just a system of 4 plates with 2 of them short circuited. So the battery is not playing any role till the switch is closed. So you don't have to worry about that. So you know that when this system is given a charge like this, that the net charge on these plates is like this. What will happen is the net charge of the whole system is plus Q naught. So Q naught by 2 and Q naught by 2 will come on these two surfaces. Okay. So naturally there will be minus Q naught by 2 here induced, minus Q naught by 2 here induced. Okay. And sorry, just a minute. Minus Q naught by 2 here. This surface will have minus Q naught by 2. And these two surfaces will have plus Q naught by 2. So this will be minus q naught by 2 because the net charge of this is 0. This is minus q naught by 2, and this is plus q naught by 2, and this is plus q naught by 2. Okay. So as a result of this, this will have some potential difference. This will have some potential difference. So if this is plate 1, 2, 3, and 4, you can see that the electric field will be in this sort of direction. So V1 minus V2, or in fact let's okay, V1 minus V2 will become minus of Q naught upon 2 epsilon naught A into D, and V3 minus V4 will be plus of Q naught upon 2 epsilon naught A into 0.8 D, because this distance is 0.8. This is D. Okay. So this will become, as you can see, Q naught was how much? 24. So 12 divided by 16. So minus 3 by 4 volts. And this will become 3 by 4 into 0.8. So 3 by 5 volts. Like this. So this will be the state before you close the switch. Okay. No, see, that is the thing now. Without understanding the charge distribution, you can't find out the energy now. Yeah, you can calculate the energy directly from Q square by 2C method also. But to understand how charge is flowing through, you will have to understand the distribution of charge. Yeah, so you can calculate the initial potential energy without even the potential differences. That's okay. So initial potential energy will be Q naught by 2 whole square by 2C1 plus Q naught by 2 whole square by 2C2, where C1 is epsilon naught A by D is 16 microfarad, and C2 is epsilon naught A by 0.8 D. So that is 16 into 5 by 4, so 20 microfarad. Okay, so you can do that. That's correct. Okay, so you can calculate the initial energy this way. Now, afterwards, what's going to happen? Now, here you have to think very carefully, because what's going to happen is that this system of plates in between will have a conserved amount of charge. Okay, so with the battery connected, let's say the battery has supplied Q amount of charge like this. So it's like now this plate is having plus Q, this plate is having some Q1, This is having some Q2. This is having minus Q, where Q1 plus Q2 is plus Q0 from conservation of charge, which was plus 16 microcoulombs, or whatever that charge I had given, I don't remember. Okay, and okay. So you'll have some kind of a system like this. Sorry, 24 microcoulombs this was. And epsilon naught E by D was 16 microcoulombs, and the EMF of the cell was given to us as 20 volts. Okay. So the thing you have to understand is what will be the distribution of charge like. So these two sides still have to have, okay, plus Q0 by 2 and plus Q0 by 2. But this side now suppose has plus Q1 and minus Q1, and this side has plus Q2 and minus Q2. Okay. So now we will have this constraint relation that Q2 minus Q1 is equal to this capital Q1 plus Q2, which is basically equal to plus Q0. Okay. That is this thing. And Q by 2, or rather Q0 by 2 plus Q1 is plus Q. Then from the other side, minus Q2 plus Q0 by 2 should be equal to minus Q. Okay. Because Q is the charge circulated by the battery. Okay. And then this potential difference plus this potential difference has to be equal to the EMF. So Q1 upon epsilon naught A into D plus Q2 upon epsilon naught A into 0.8D, whatever. This has to be equal to E. So these are the equations we have to solve in the system to find out the final energy in all this. Now see, the concept, Bhaumik, is always that total charge is conserved. Okay. Battery only circulates charge, so the total charge of the system will remain Q1, capital Q1 plus capital Q2, which is plus Q0. And facing side should have equal and opposite charge. Okay. And the outer two sides will always have the same amount of charge. So it's happening from induced charge. See, now minus Q charge is getting supplied to the fourth plate, no? That's why. So let's see what our equations are becoming from here. So we are getting Q2 minus Q1 is equal to plus 24 microcoulombs. That's our first equation from here. Now let's say these are equations 2 and 3. Okay. So 12 plus Q1 is equal to plus Q, and 12 minus Q2 is equal to minus Q. Which also basically tells us that, I mean, this equation can be confirmed by adding these two, or rather subtracting these two or whatever, by adding these two. If you add these two equations, you confirm equation 1. And now this equation will become like this: Q1 upon 16 plus Q2 upon 20 has to be equal to 20 volts. That's our fourth equation. So solving these, what we have to find? We have to find Q1 and Q2, which basically you can just get by equation 1 and 4, because 2 and 3 are anyway dependent on these equations. Okay. So just solve 1 and 4 to get Q1 and Q2, and then you will also find the value of Q. So from that you will find the work done by the cell. It is Q into EMF, because that's the charge circulated. And from Q1 and Q2 you will find the energy in the two capacitors. So you'll find the change in potential energy, and that's it. That's how you solve this. So the reason why I brought up this question, people, is because traditionally we think when we have series combination of capacitors now, they should have the same magnitude of charge on the inner plates. But here that is not happening, because the inner two plates have been given some net charge from before. Exactly the point. That is the point I was making, Aditya. कि यहाँ पे ना वो नहीं होगा. Q1 will not be equal to Q2. Why? Because there is some net charge on the plate 2 and 3 put together. Yeah, so let's run through the equations once more, Aditya. So this is actually more a question about, electric field and redistribution of charge and things like that. So see what is happening here is that initially you had a system like this, जिसको मैं मैंने ऐसा चार्ज दिया था. This was given Q naught, so 0. Okay, so they had to just redistribute in such a way that equal charge comes here, okay, and then equal and opposite charge comes here, because this one's net charge is 0. So okay, and therefore this kind of charge comes here. You can see everything is satisfied nicely as long as this is plus Q naught by 2, this is plus Q naught by 2, so this is minus Q naught by 2, this is plus Q naught by 2, this is plus Q naught by 2, this is minus Q naught by 2. So if you see our 4 plates, 1, 2, 3 and 4, they satisfy the condition that the charge on plate 2 plus plate 3 is plus Q naught, because they are short circuited, and you have given this a net charge of Q naught. Okay, and you can see that it follows the principle that facing sides have equal and opposite charge, and the outer 2 sides have equal charge. So that means the electric field inside all the plates is going to be 0. It will take care of itself, that condition. So here we will have electric field like this in this region. We'll have electric field like this in this region. Okay, we'll have some electric field like this in this region, and we'll have some electric field like this in this region. But there won't be any electric field inside any of the plates, and there won't be any electric field in this region here also, because the potential of plate 2 has to be equal to the potential of plate 3. So there should be no electric field in between them. Okay. Now, when you connect the battery, the only thing that the battery is really doing is that it is giving your plate 1 some charge plus Q, and your plate 4 some charge minus Q, till the potential difference sum becomes equal to the EMF of the cell. And that's all that's happening. Cell is like an external agent जो ये पूरे सिस्टम को ऐसा चार्ज प्रोवाइड कर रहा है that it's giving some net charge Q to this and taking away some net charge from this, so that the net charge of this plate now becomes plus Q, the net charge of this plate becomes minus Q, and let's say the charge of these 2 plates are Q1 and Q2, but that will be such that Q1 plus Q2 will have to remain conserved at plus Q naught. Okay. But what is the condition on how much charge the battery is going to provide? The condition on that is that the potential difference V1 minus V4 should become equal to the EMF of the cell. That is the condition. Okay. So for that to happen, now you can see the whole system's net charge is plus Q naught. The charge on, so now in my new steady state, the sum of the charges on all 4 plates put together, that is equal to how much? That is still equal to plus Q naught. Okay. So that is why by that limiting condition, or by that steady state condition, you know that these 2 sides will have to have plus Q naught by 2 and plus Q naught by 2. But now these 2 pairs will have some different amount of charge. So let's say this one has some plus Q1 and this one has minus Q1. So this has some different value now. This has some plus small q2 and minus small q2. So you can see that this is generating an electric field according to this value. This is generating an electric field according to this value. So this potential difference that we've written now, V1 minus V2 plus V3 minus V4. This has to be equal to the EMF. This is the main thing. Okay. Of course, the potential of plate 2 is equal to the potential of plate 3, which you're also showing there's no electric field between them. Okay, so now this is the net thing. So rest of the things is just conservation of charge. Okay. So from conservation of charge, you can see that the charge on plate 2 plus 3, which was equal to plus Q naught. Now that is equal to actually minus Q1 plus Q2. Okay, so that's our first equation, that Q2 minus Q1 is equal to plus Q0, which was 24. Just a second. Yeah, so this is equal to 24 microcoulomb. So that's like our first equation. Okay, and then this thing. This will give us our second required equation, that Q1 upon epsilon naught A into D plus Q2 upon epsilon naught A into 0.8 D, because it just so happens that this plate gap is 0.8 and this is D. So this has to be equal to E. So this will give us our second equation, that Q1 upon 16 microfarad plus Q2 upon 20 microfarads has to be equal to 20 volts. So actually solving these two will give us what we require. We will get the value of Q1 and Q2 from this. And once we get the value of Q1 and Q2, you can see that Q, small q, is equal to the charge which this plate gains, which is 0 before anything had happened. So plus Q1. And that should be equal to the charge that this plate gains, the fourth one. Okay, this is plate 1. This will be plate 4. So that will be equal to minus Q2 plus Q0 by 2. Okay, so you can see that these will be self-explanatory, because these will also be the result of equation 1 and 2. So these two equations are basically consistent with these two equations. Okay, so just let's solve this now. Substitute this here. So Q1 by 16 plus Q2, which we can write as 24 plus Q1 by 20 should be equal to 20. So oh, sorry, my mistake. Okay, so this will be our Q1. From this we'll get Q2 as 24 plus Q1, and from that we will know the final energy stored is Q1 square by 2C1 plus Q2 square by 2C2, where C1 is 16 microfarad and C2 is 20 microfarad. Okay. So from this we will get the change in potential energy as the final minus the initial. Initial we had calculated earlier. Okay, and from this we will get the charge circulated by the battery. So Q will come as 12 plus Q1. So from this we'll get the work done by the cell is equal to Q into EMF. So then the heat dissipated will become the work done by the cell minus delta U. Yeah, coming up, don't worry. So the values are a little lengthy in this, so don't worry about that. The main thing is the concept of the question. Okay. Okay, now next example for us today. This question. Sorry. Now we'll do something interesting involving concept of okay, so this is a frictionless surface below. This is a smooth surface. Okay. But this has a coefficient of friction 0.6. Okay. And this is a plank of mass 10 kg. Now what we do is we put a spinning cylinder on it. So you put a cylinder spinning at an angular speed initially. So this one's mass is 2 kilograms and radius is 50 centimeters. It has an angular speed initially omega naught. So at t equal to 0, a spinning cylinder at an angular speed of 10 radians per second is placed on the plank. Okay. Assume the plank is very long. So find the velocity of the center of mass of the cylinder and velocity of the plank when slipping ceases. Okay. Assume the plank to be very long. So the cylinder doesn't roll off before slipping ceases. Then find the time for which friction acts. For this you need the value of G, so take it as 10 meters per second square. And also find the work done by friction, the total work done by friction. So there are several ways of doing this question, but there is one way which is the easiest by using conservation principles, but you have to be very careful about what conservation principles you can use. Okay, so if you're working on it, just continue. I'm just helping you out with the free body diagram. So what will happen is, because of the clockwise spin on this, there will be kinetic friction acting like this. Because on this, at the point of contact, there will be kinetic friction acting like this till the slipping stops. Okay. So the velocity of the plank is 5/16, and the cylinder is, this is in meters per second. Okay. Yeah, I will just verify the answer. Just give me a moment. How much is R omega? Omega is 0.5 into 10. So 5. Yeah, it seems correct. Okay, so this is the basic force picture. Okay, so now what we'll understand is that if you take the plank plus cylinder as a system, then linear momentum of the system is conserved. It is conserved. Okay, so if when you started out, this is at some intermediate time, but when you started out, this was only spinning, and this was at rest. So linear momentum of the system was 0. And when the rolling has started, at that point of time, if this is having a final velocity v prime, let's say, and this is having a final velocity v double prime, this is having omega prime, okay, then mv prime minus capital mv prime should be 0. So this will give us my first equation. This is when there is no slipping, and this is at t equal to 0. That's one thing. Okay, now the other thing is very interesting here, that if I take any point anywhere on this horizontal plane like this, okay, then for the cylinder, I can conserve angular momentum about that point. So angular momentum for the cylinder, not for the system, but for the cylinder about O is conserved. Why, you can understand from the diagram here. Okay. So what is happening on the cylinder, if you see, mg and normal reactions line of action are same, and they are cancelling each other. So their torques are also cancelling each other. This normal reaction and mg, their torques are also cancelling each other, whereas the line of action of friction is passing through that point. which I have taken on this plane. So you can see that torque about that O is 0 on the cylinder. Okay. Now, mind you, for the whole system, it will not be conserved because this N prime and Mg, their line of action is not the same, and that line of action of N prime is constantly changing. Okay. So that's what makes the problem very interesting. Angular momentum for the whole system will not be conserved, but only for the cylinder alone about that point will be conserved. So my final angular momentum about this point P, oh, I've named it O. Okay, so I'll just take this point as O. So about this point O, my final angular momentum is small m v prime r clockwise plus I omega prime clockwise. That should be equal to I omega naught clockwise. Okay. So we have mv prime r plus mr square by 2 omega prime is equal to mr square by 2 omega naught, or we have v plus r omega by 2 is equal to r omega naught by 2. So this is our second equation. Okay, and mind you, here v prime is not equal to r omega. Now we come to the no slipping condition. So the no slipping condition is what? That standing on the plank, it should look like to you the cylinder is rolling. So with respect to you, the relative velocity of the cylinder center will be v prime plus v double prime. Okay, and this point of contact should be at rest. So Vp should be 0 in the Planck's frame. Okay, so the relative velocity of the center of mass of the cylinder should be equal to r omega prime. This is when rolling has started. Okay, so v prime plus v double prime is equal to r omega prime. This is our rolling constraint. So now this system of three equations has to be solved. This is the easiest way of doing the question. You can do the question by impulse momentum, by force and torque and all that, and you can generate some time-based equations, and it will become a bit lengthier, and you can come to the same conclusion by that also. But this is the easiest way of solving it, as I'm telling you. Okay. So this system of three equations we have to solve now. Okay. So it's very easy. You substitute this over here. Okay. So you will get v prime plus v prime by 5 is equal to r omega prime. So v prime will be equal to 5 by 6 r omega prime. And then substitute that in equation 2. So you will get five by 6 plus half by 2. So 8 by 6 omega prime is omega naught by 2. So we will get omega prime as 3 by 8 omega naught. So once you got that, we'll get v prime as 5 by 6 into 3 by 8. That is 5 by 16 r omega naught. And therefore we'll get v double prime as 1/5 of that by 16. Okay. and r omega naught itself was equal to 0.5 into 50 centimeters, so 0.5 into 10 radians per second, so that's 5 meters per second. So this will become 25 by 16, and this will become 5 by 16 meters per second. Yes, Ganesh, that's correct. Very good. Okay. So this is what we are getting finally, that from this state initially, where this just had a spin of omega naught, finally when rolling starts, this will go backwards. Some point of time when rolling starts, so these are the values. So omega naught was 10 radians per second, and r was 0.5 centimeters. So we are getting v prime as 25 by 16 and v double prime as 5 by 16. Getting all this. So basically, we're getting omega prime as 3 by 8 omega naught, and v prime as 5 by 16 r omega naught. Parametrically, these are the values here. So now it's actually very interesting that we can go backwards and calculate the time taken, because we can also understand that in the free body diagram, mu mg kinetic friction is acting on this from t equal to 0 till some time, let's say t equal to t1, when this speed becomes v prime and this becomes omega prime. Okay. Then kinetic friction stops acting after this. So during this period, okay, the acceleration was mu g, and after this now the acceleration is 0, because friction will stop acting. So this will just continue at v prime. So we can use this now, that v prime is equal to mu gt. So the time for which friction acts is actually v prime by mu g, which is 25 by 16 divided by mu, I think was 0.6 or something. This will become 6 in seconds. So for a very short duration, you can see that time is active. This is the time for which friction acts. This is the time, okay? So I will just take you through my conservation equations once more. Then we'll also calculate the last part, the work done by friction. Now I'll also discuss how you can do this by a more fundamental method without using conservation principles, but rather by using impulse momentum concepts. And of course, no slipping condition finally. One important thing here, that for this system, as the plank plus cylinder, okay, angular momentum about O is not conserved. Okay, because in the above diagram you can see N prime and Mg don't act along the same line of action. This is something we have to be careful about. Okay, and as far as the work done by friction is concerned, the only practical way in which you can calculate it, which is more or less feasible, is by using work energy. The work done by friction should be equal to the change in kinetic energy in the system, because normal reactions and weights are not doing work, because they are acting through points whose displacement is perpendicular to the direction of the force. Okay? So for the whole system, so the work done by kinetic friction on the block or plank or whatever, plus work done by kinetic friction on the cylinder put together, that is equal to the change in kinetic energy of the system. Or individually also you can say that work done by friction on the plank is equal to change in kinetic energy of the plank. So yes, this is a situation where kinetic friction is doing positive work on one of the two parts. But again, the total work done by kinetic friction will be negative, we'll see. Because it will be doing more negative work on the cylinder than it is doing positive work on the plank. So it's still a dissipative force in general. So individually this equation will also hold, but for us this is more important right now. So the total work done by friction, this thing, that will be equal to half mv prime square plus half mr square by 2 into omega prime square plus half capital M V double prime square minus half mr square by 2 omega naught square. So this is how we'll have to calculate this. Okay, I'm not getting into this, it will take time. But when you do this now, you'll see this will come out to be a negative quantity. Whereas in these equations, this will be negative. Okay, but this will be a positive quantity. But when you sum these up, the total will still be negative. Now I'll quickly discuss the other way you can do this question. You can go through these equations later. I'll send you the notes, so don't worry. Because you see, you can get a lot of conceptual questions as options and MCQ questions in this. Now, so you have to be very careful and clear about all the concepts, not just the numerical calculation. So whether kinetic friction is acting like a dissipative force here, is it doing positive work on the plank? Yes, it is doing positive work. It seems very odd, but yes, it's doing positive work. But overall on the system, it is doing negative work. Okay, so like that. So to be careful, clear about all these things. Okay. Now the other way of doing the question is just by dynamics. So what you do is you understand that this is the only important force which is creating linear acceleration and angular deceleration for this. Okay. So A is equal to mu g, and alpha will become mu mg r divided by mr square by 2. So you'll see it will become 2 mu g divided by r. So if this started at t equal to 0 with only spin, okay, this was the state at t equal to 0. So at some intermediate time, this has a speed v1 and an angular speed omega. So you can see that v1 will be equal to mu gt and omega will be equal to omega naught minus 2 mu g by r into t. Okay, because this is creating a reverse angular acceleration like this. Okay, whereas on the plank, friction is acting like this. Okay, so it has an acceleration, let's say a prime mu mg by capital M. So that will become mu g by 5. Okay, so if this started from rest at t equal to 0, then at some time t is having a speed, let's say v prime. Now don't confuse this v prime with that v prime. Okay, or let's write this as v2 so that we don't confuse these things. Okay, so this has some speed v2 at some time t will be a prime into t, so that is mu g by 5 into t. So we have these equations now. Now you see the rolling condition. So you can solve it very easily by this also. So when rolling starts, v1 omega v2. So you can see that even you don't even need to get into relative motion. You can just see that this point's velocity should be equal to this point's velocity. So in the ground frame only, ground frame, you can see that velocity of the point P should be backwards, should be minus v2 like this. Okay, so minus r omega plus v1 should be equal to minus v2. Or you'll get that relation that v1 plus v2 is equal to r omega. Okay. Now you substitute all this over here. So you get the time first. Okay. So v1 is mu gt, v2 is mu gt by 5 is equal to r omega, which is omega naught minus this. Okay. So we will get 6 by 5 mu gt, and then from this side plus 2 mu gt is equal to r omega naught. So this is becoming 6 plus 10, 16 by 5 mu gt is equal to r omega naught. So this whole variable mu gt is 5 by 16 r omega naught. So now you can see that your final speed when rolling starts, okay, this is when rolling starts or it stops to slip. So you can see that your final speed v1 will be mu gt, so that is 5 by 16 r omega naught, and v2 will be 1/5 of that. This is mu gt, this is mu gt by 5, so it will be r omega naught by 16, and these are the answers you had got earlier also. Okay. And your omega you can see from here is v1 plus v2 by r, so that is 6 by 16 r omega naught or 3 by 8 r omega. So these are the values you'll notice you had got earlier. V prime, V double prime and omega prime, they were these values only. So there's another way of solving it by using dynamics. So these values. All right, so that's about 2 ways of solving this question. Okay, next, want to do a question in, yeah, I will go through it someday. Okay, so while I'm going through that, just try out this next question. So this is the horizontal ground level, and we have a uniform horizontal magnetic field. Like this over here. So this is our thing. Gravity is acting along the negative y-axis. So y-axis is your vertical. J cap is your vertical direction. Okay? And there's a uniform magnetic field. In fact, horizontal magnetic field going into the plane. So minus B naught K cap. Now this is the ground. So what we're doing is a charged particle is dropped from some height h. So if Q is equal to 50 microcoulombs, M is equal to 20 grams, G is equal to 10 meters per second square, and the magnetic field has a magnitude of 200 Tesla. You have to find the minimum height from which you should drop it so that it does not hit the ground. Okay. Find the minimum height from which the particle can be dropped such that it does not hit the floor or the ground. So that's one thing. Then in this case, how much will be its maximum speed? Okay. And third, find its acceleration vector in unit vector notation at an instant when its speed is half the maximum speed. Okay. So just start working on this question. The hint to you is, just start working on it, then I'll give you a hint. Ganesh, just check your answers once. It is cycloidal motion. Okay. Yeah, H is correct. V max, I think you have to check once. Okay. It's cycloidal motion. You have understood this much, na, beta? Okay, so I'll just quickly take you through the basic ideas. So you'll remember that if we had a situation of crossed electromagnetic field, then the motion we had proved was cycloidal motion. So for example, if we had a magnetic field like this, uniform, and we had electric field like this, suppose, we had a uniform electric magnet and no gravity, then a charged particle released from rest over here, it would initially have an acceleration of QE by M like this, okay, and then it would start to bend because of its velocity in the upward direction. So V cross B would be in this case towards the left. So it would start to bend like this, and it would go in a motion like this. Okay. It's not semicircular; it's actually cycloidal. Okay, so at some general time, if its velocity was like this, then there would be magnetic force like this on it always, and there would be electrostatic force always like this on it. Okay, till it would reach this point where it would have the maximum velocity. And at that point of time, the magnetic force would be like this, and electrostatic force would be like this. Okay. Now, once you do the derivation of this, now you will come to know the basic relations, how it works out. If this is your y-axis and this is your x-axis, then what is happening is it's basically like a rolling motion in this direction. It's like a case of v and omega in this point starting from here. So when it reaches here, it's 2v, like that kind of thing. Okay. So one of the features of this cycloidal motion is that the magnitude of acceleration is always the same. So at this point of time, the acceleration magnitude will be the same as the magnitude of acceleration at this point of time, but the direction will be opposite. So that's one thing, that in cycloidal motion, magnitude of acceleration remains constant always. Okay. And the second thing is that the work done by electrostatic force is equal to the change in kinetic energy, because work done by magnetic force is zero. So over here, if the y component of displacement is so much, then starting from rest over here, here the speed is v. So we have qey is equal to half mv square. So many a time we don't need to use the entire equation of cycloidal motion and all to solve. Just these tricks are enough to solve. Okay. Whereas if you're going for the equation of cycloidal motion, then you can see that the velocity at any point of time will be this sorry, it will be E by B into 1 minus cos omega t I cap plus this kind of term, the velocity will be. And the displacement will be this kind of a thing, So from this you can see that the maximum displacement is this kind of term and all that. And there is a term for omega and all that you can compare. Okay. But here we will not solve by this method. We'll do it by the very easy comparison method. So here also it's cycloidal motion only, but the difference is that the role played by mg is the role played by electrostatic force over here. So the initial acceleration is g downwards, but then the magnetic force into the plane and the fact that this is positively charged means that in this case v cross b is pointing like this, so the path will be cycloidal like this. So suppose it reaches that point where it turns before it hits the ground. That is the condition that we want, that before it hits the ground it should reach that point where it turns. So wherever it turns, its speed will also be maximum and its vertical displacement will also be maximum. The magnitude of vertical displacement will also be maximum. So that is this point over here, let's say. So when it reaches here, it is having the maximum vertical displacement, which we can take as h or y max or whatever. Okay. So at that point of time, it has the maximum speed. Now the important thing is when it has the maximum speed, the magnetic force acting on it, q v max into b, should be exactly double of the gravitational force, because that property of cycloidal motion becomes important, that this will still have the same magnitude of acceleration. So first equation that we have is q into v max into b minus mg by m has to be equal to a naught, which is g. So that will basically tell you that q into v max into b is equal to 2mg, or the maximum speed, provided it does not hit the ground before it reaches the maximum speed, is 2mg by qb. This is the maximum speed. Okay. Now the other thing is the minimum height from which it will, this thing. So here the work done by mg is equal to the change in kinetic energy, or we can even say that change in kinetic energy plus change in gravitational potential energy is 0, because work done by magnetic force is 0. Okay, so starting from rest over here, of course. So half m v max square is equal to mgh. Okay. So h is equal to v max square by 2g. So we'll substitute that over here. Okay. So the minimum height from which we should drop it should become 2 times m square g by q square b square. So Ganesh, I think this value you had got. It is actually like, very interesting thing. Along the y-axis, there is SHM happening. Along the x-axis, it's like a superposition of linear and SHM. Uniform motion and SHM. So, the way to relate this is not to always remember that the rolling wala cycloidal motion, that's the easy thing to relate it with. If you look at the cycloidal motion in case of rolling, and you just know that, okay, in the case of magnetism, funnily enough, because there is no connection between that mechanical forces that act in the case of rolling and the electromagnetic forces that act in the case of the cross electromagnetic field, seemingly there's no connection between them, but it just happens that way. So this cycloidal motion we are talking about is when there is pure rolling, that is rolling without acceleration. So v naught is equal to r omega naught, and acceleration of center of mass is 0, angular acceleration about center of mass is 0. So this point over here, at t equal to 0, the velocity of the point is 0 when it starts from here. So by the time this point now reaches somewhere here, let's say, okay, this angle theta has become omega t. Okay, and its velocity will become the vector sum of this r omega and this vc, because of this. So at time t, you can see that the velocity of the point P, it becomes like this. It becomes V naught minus R omega see here that this will be theta. Okay. So the velocity is this kind of a term. It is V naught 1 minus cos omega t I cap plus V naught sine omega t j cap. Okay. So if this point was where you started from, so when it reaches here, the displacement, if you write it as some x I cap plus y j cap, you'll understand what is happening. The displacement is x I cap plus y j cap, where the x coordinate is the integration of this. So that will actually give you a term like this. It will give you v naught t plus sine omega t by t. Sorry, sine omega t by omega v naught. Like this. So it's not an SHM. This one is a perpetual motion. So you can see that your x component of velocity ranges between 2v naught and 0. So that means it never has negative x displacement. It's always going like a start, stop, start, stop, start, stop kind of motion along the x-axis. But along the y-axis, you integrate this term and you can see that you will get along the y-axis is doing this. It's going from 0 to maximum height, then coming back to 0, then maximum height. So the combination of the two gives you the cycloidal motion. It's like this. Which is why the cycloidal motion is never like this, because it never comes back. That's not correct. The cycloidal motion is like this. It comes to rest over here and has a maximum speed over here. Okay. So your y is like this. V naught 1 minus sine omega t. You'll get that by integrating that vy term. So you can see your Vx is V naught 1 minus cos omega t, like this, and your Vy is V naught sine omega t. So this is an SHM. The vertical motion is an SHM, but this is not an SHM. Okay, so that type of motion. And how we know that that acceleration thing is because like this, that now you see that if you look at this point P, okay, the acceleration of the point P with respect to the center of mass is centripetal acceleration for uniform circular motion. Okay, so it is always omega square r, okay, along minus r cap. So the acceleration of the point P in the center of mass's frame has a constant magnitude. Is uniform in magnitude. Now the center of mass is what type of frame? It's an inertial frame because acceleration of the center of mass is 0. So that means the acceleration of the point P in the ground frame the same as the acceleration of the point P with respect to the center of mass frame, which is uniform. Okay, so that is what tells me कि ये वाले picture में जितना उसका acceleration है, यहाँ पर भी उतना ही acceleration है in magnitude. And later when it reaches this point here, it will have the maximum speed. That's also easy to prove actually. If you calculate the magnitude of this and maximize it, you can show that this 2v naught will be the maximum value of v. But even at this point of time, its acceleration is the same. It's equal to v naught square by r, or r omega naught square in magnitude. So all these properties of cycloidal motion become very useful when we do the cross thing of that. So, you can derive the entire cycloidal motion by just remembering these facts. You don't have to actually derive from the forces and all that. So, यहाँ पे, for example, ये h जो है ना, this h is like a 2r. So, the r of the cycloidal motion is like m square g upon q square b square. Okay, and this v max is like a 2v naught. So, your v naught is equal to mg upon qb. Okay. So now you can also see that your omega of the cycloidal motion is v naught by r. So that's another way. If you want to derive all the things, you can derive it that way also. But here we just required these two things. So we got this. This is the minimum height from which it should be dropped, and this is the maximum speed it will achieve. Okay. Now the next part is interesting actually. So वहाँ पे क्या हो रहा है? You have to, the magnitude of the acceleration will be always this v naught square by r. So you've got v naught from here and you've got r from here. So the magnitude of that acceleration of that point will always be v naught square by r. So that will be mg square by q square b square by this r, which is m square g by q square b square. So that you can see will be g. But it's just a matter of coincidence, and I'm showing you that. So the magnitude of the acceleration will always be g at all times. But I ask you to find the acceleration as a vector quantity at the instant when v is equal to the magnitude of v is half of v max. So again, the geometry of cycloidal motion is little important for this. You have to figure out at which point of time, in terms of its trajectory, is going to have this speed which is exactly half the magnitude of the maximum. And therefore, at that point of time, where the acceleration vector will be pointing. Okay, so this part is going to be a bit time taking, so you can figure it out. Okay, because basically you'll have to relate this cycloidal motion with this diagram here below. You'll have to try and understand that somewhere over here, when its speed becomes half of this, so you'll imagine that this particle is on actually a cylinder which is rolling upside down on this surface. It's doing this. So that's why this particle is going like this. You have to think of it like this, that is rolling on this kind of surface. You're seeing it upside down. Anyhow, in JEE, you cannot expect questions of that level of toughness, where that direction of acceleration and all is required. Typically, you'll be asked these two things: the maximum speed, the maximum displacement along the gravitational field or electric field, and all that. And that's for that only I have brought to your notice these two tricks that you can use, so that you don't have to derive the entire equation of cycloidal motion or memorize it or anything. You just remember these two simple facts: that magnetic force does not do work. So whether it is electrostatic force or gravitational force, that is the one that is doing work to change the kinetic energy, and that the magnitude of acceleration will be the same in the two extremes of the cycloidal motion, that is at the rest position and when it reaches the maximum speed position. So at the maximum speed position, the magnetic force will become the double of whatever the other forces, whether it is mg or qe. So that's an important trick to remember. Okay, so you can figure that v by 2 part or the v max by 2 part yourself. Okay, I will just give you a quick hint for that. Then see, in this rolling, in this case, now when does the speed of this point reach half of, I mean half of the maximum? When its magnitude should be equal to v naught only, no? So r omega and v naught's vector sum should be equal to v naught, so that means they should be at 120 degrees. The angle between your r omega and v naught should be 120 degrees. So it will be somewhere here, okay, where v naught is like this and r omega is like this, and this angle should be 120. So at that point, the net velocity of this will have the same magnitude of v naught, which is v max by 2, because v max is equal to 2 v naught. So from this, so this will be one possible point, and another possible point will be somewhere here, the symmetrical point over here. जब ऐसा होगा, r omega and v naught are again at an angle of 120 degrees. So that's the interesting thing. When the angle between these two vectors is 120, then where is your centripetal acceleration line? So that will give you the direction of the unit vector. So it's that kind of geometrical problem actually. Okay, now Somadeep, I'm just referring to the question you have sent. I want to discuss that. It's a very, it's a, it's a concept from this one, what we call modulation of waves in communication theory. So you just need to go through that once. हाँ, Ganesh, I'll repeat that. So क्या हो रहा है ना, देखो मेरा VP जो है ना, it is always the vector sum of these two things ना. The instantaneous velocity of that point, it is the vector. Now I'm talking about rolling wala cycloidal motion. Okay, you can relate that with that charge particle one later. Okay. So the velocity of this point P in general is the vector sum of the velocity of the point P with respect to the center of mass plus the velocity of the center of mass. So in this thing, it is some r omega into some unit vector, let's say n cap plus v naught I cap. Okay. Now I want that this should become equal to half of v max. So that means it should become equal to v naught. So I'm looking for a vector diagram where the vector sum of v naught and r omega, which are actually equal vectors, should be equal to v naught. So that is happening when this is this one, when this is 120 degrees. So this is, so when this angle is 120, this VP will become v naught. Got it, na Ganesh? Okay, so that condition. So that will be once over here and once somewhere over here. When it later comes somewhere here, so then your r omega is like this and VP is like this. So if this angle is 120 again, and again at this point of time, the net speed will be v naught in that. Anywhere else you will see that will not happen. Okay, I will just switch screens for a moment because this question I want to discuss. Okay, so now see, यहाँ पे what is given to us is, this is signal containing multiple frequencies is shown in figure A. It is passed through two different filters and the outputs are shown as B and C. Okay. Now see, first thing you have to do here is you have to recognize that what kind of signal is A. I mean, obviously it is a mix of frequencies, but what kind of modulation is happening over here? It is frequency modulation or amplitude modulation. Yeah, Bhavik will come to the answer. Okay, don't worry. But what I'm saying first is ki how will we interpret ki A mein kya ho raha hai? How are we actually mixing the signals? There's obviously, you know, remember in communication theory, we had discussed that there is the modulation. So you have the carrier wave, which is high frequency, and you have the modulating wave or the signal, and then you get the modulated wave. Okay. So what are the different methods? There's frequency modulation, there's amplitude modulation, there's phase modulation. Okay. So this one is what? It's amplitude modulation. You can see it is amplitude modulation. Okay. Now see, if you remove the low frequency partner, that is the signal part, you're left with only the carrier wave, and the carrier wave is a high frequency wave with less amplitude. So that is this one. So in this, what you've done is that from the mixed wave, you remove which part? The low frequency part. Okay, because you are getting this by mixing a wave like this with a wave like this, but via amplitude modulation. So when you do amplitude modulation for this, okay, then this modulates this one's amplitude. So it becomes like this. Okay, I will come to that, Ganesh. Okay. So, but before that, so in this, what we are doing, we are removing the low frequency. So removing the low frequency means what? High pass filter. We are allowing high frequency to pass. Low frequency is cut. So C corresponds to this thing, high pass filter. So passing through a high pass filter. And in this, see what is happening. The modulating frequency appears to be less than the modulating frequency here. So if there were multiple modulating frequencies, then the higher one has been removed, no? Because there's a slower variation. So this is a low pass filter. You're allowing the high frequency to get cut. I mean, you're cutting the high frequency and allowing the low frequencies to pass. So B should correspond to low pass filter and B should correspond to high pass filter. So yes, your answer was correct. Yeah, Ganesh, I'm coming to your question, but is this clear? Somadeep? Yeah, एक बार ना, not even the chapter. You just go through this thing, no? The what we call the diagrams for the graphs of all this phase modulation, amplitude modulation, and frequency modulation. Okay, in communication theory, or you can just go through my lecture notes also. All that will be there in that. Okay. Yeah. Now, Ganesh, coming to your question, uh, what will happen when? Just a minute. Come back to your question. Yeah. When we bring the source slit closer to the double slits in YDSE, what effect that has on the fringes? So basically, see what will happen is that the illumination of the two slits S1 and S2 will increase. The intensity of light that is incident on these two, na, if this is further away, okay, here also they are in phase and they are what we call coherent. But when we bring it closer, same thing, they are in phase and coherent. But what is happening is that the intensity is increasing. Your I1 is equal to I2 is equal to I0 in both the cases. But in the second case, this I0 is increased. So the fringe pattern will be the same. Fringe width will be the same. But the brightness of the bright fringes will increase. The dark fringes will still be completely dark, assuming the slit widths are the same and all that. So there is no difference in the fringe width. There's no difference in the position of the fringes. The only difference is that the bright fringes will become brighter in intensity. Send me the question. Mother, is there anything specific closer to the double slits? How much closer? No? That also. Okay, and also depends on the source of the question. I mean, there might be some kind of limiting condition up to how close we can bring it to maintain that coherence. But I don't think that is significant over here. Like for example, if we bring the slit right over here, then it's a tricky situation what might happen. Okay, because your interpretation of secondary wavefronts and all might really depend, but it depends on whether this distance is now close to the wavelength of light or so. It's a bit tricky that way, but in general, this distance, we are still assuming that this distance is large compared to small d. It's just that you're changing it by some factor, like you're making it from d to, let's say, 0.75 d or something. So in that case only this will happen, the brightness will increase, nothing else will happen. Okay, let me just go through that. Ganesh, this is part of a paragraph question or? Okay. Just send me the whole paragraph. Now later I'll go through it once and tell you, because that small s by capital S ratio and all that, I need to understand what it is. Okay, I'll explain it to you. Don't worry. We have a class on Wednesday also. Achha, on Wednesday's class, some part of the lecture I will be teaching fluid mechanics, because students of non-integrated batch need to be going through that chapter. So I will teach it in such a way that if the rest of you attend, it can also be like a revision, but then it's up to you. So what I'll do is the second half of the lecture now, I will teach fluid mechanics. Okay, second, I will remind you about this in the groups on Wednesday. But the second hour of the lecture, I will teach fluid mechanics. First hour and a half, I will discuss your doubts, depending on how many doubts you have, otherwise questions. So that's it for today's session, people. Wish you all the best.